In Module 5 of Ohm's Law, Power Law, Rules and Theories, we'll be discussing circuit analysis. Circuit analysis is the process of solving a group of independent equations to determine the voltage drop, current, resistance, and wattage at each element in the circuit. In Module 4, where we explored series parallel circuits, we used circuit analysis to arrive at the values for each resistor. In this simple method that we'll present here, it does not require algebra or complicated math. It's done more with matrix forms. We use the information we calculate to design the operating values of each component and for troubleshooting, testing, and quality control. These values determine the wattage, current, and voltage each element must be able to handle. For example, we may know the resistance value of each circuit component, but we must also know the wattage that will be present at each component to determine and choose the correct wattage. A resistor drawing 1.3 watts would require a quarter-watt resistor. A component rated for 50 volts will not handle a 120-volt supply. An LED light that has a current limit of 20 milliamps, 0.020 amps, cannot handle a current draw of 0.2 amps. Undersized components will burn out. We use circuit analysis then for three main reasons: to size the components, use the calculated values to test the circuit for troubleshooting, and then for quality control. So now let's look at Circuit 2 from Module 4, Series Parallel Circuit. In this circuit we have two resistors, R1 and R2. They're both 1200 ohms each, and they're in series with a group of three resistors which are in parallel, R3, R4, R5 being in parallel. We have a circuit voltage, supply voltage of 28 volts. In general, it's best to start at the farthest end from the voltage source. The goal is to continuously simplify the circuit until there is only one equivalent total resistor. We need to calculate the parallel section of the circuit separately from the series portions. Here, in this case, we have the formula for a resistance in parallel. We must use the formula because we have no idea what the voltage drop is going to be across those parallel resistors at this point, because it's determined by the R1 and R2 resistors in series, and we have to know this resistor that calculates out to 400 ohms because it's proportional on the drops. We have 1 over 1 over 1200 plus 1 over 1200 plus 1 over 1200 equals, our common denominator will be 1200 ohms. 1200 will divide into 1200 one time. 1200 divides into 1200 one time, and 1200 divides into 1200 one time. 1 times 1 is 1, plus 1 plus 1 equals 3. And you remember from Module 4, all we have to do is flip this. We're going to forget this one because we're going to multiply by the reciprocal of 3 times 3 over 1200, which is 1200 over 3. And 1 times that will still be 1200 over 3. So 1200 divided by 3 equals 400 ohms. Now we set up a matrix. And this matrix, we're going to call it matrix 1. We're going to have a number of matrices. And we're going to say dash P because it tells us it's a parallel circuit. In a parallel circuit, we have certain rules, but in this case, all we don't know the voltage here again. We can't put it until we get further into this circuit. But right now we have 1200 ohms, 1200 ohms, 1200 ohms. Previous slide we determined it's 400 ohms. But whenever you have three resistors that are the same value, in this case 1200 ohms, and there's 3 of them, you just take 1200 ohms and divide by 3 and you get 400. This only works if the resistors are the same value. Here's our 2800 volts. Now we have a new matrix, and we're going to call this matrix 2-S. It's a series circuit. And what it is R1 plus R2 plus RA. All we know in RA right now is this 400 ohms. So we have 400 ohms, 1200 ohms, and 1200 ohms. This being a series circuit, we just add them up to get 2800 ohms. Using our formula wheels, take time if you have to stop this recording and copy or write this down so that you can use these formulas. It's E over I times R. If you want E, it is I times R. If you want R, it is E divided by I. And if you want I, it is E divided by R. Likewise, power. If you want power, it is I times E. If you want E, it is P divided by I. And if you want I, it is P divided by E. We're going to use those formulas. So now, using those formulas that we just looked at in a previous slide, we can start calculating. We have 28 volts divided by 2800 ohms. E divided by R equals I, and we get 0.01 amps. Using the rules for a series circuit, current is the same everywhere. So we can put this 0.01 amps, 0.01 amps, 0.01 amps at every point in this circuit. Now we can determine our voltage drop. We have E divided by R is going to give, I times R is going to give us our voltage drop. 0.01 times 1200 ohms gives us 12 volts. Same values here, 0.01 times 1200 ohms gives us 12 volts, and 0.01 times 400 ohms gives us 4 volts. 4 volts plus 12 volts plus 12 volts equals 28 volts. Our power is I times E. So we have 0.01 times 28 is going to give us 0.28 watts. 0.01 times 12 is going to give us 0.12 watts. This is the same. 0.01 times 12 is going to give us 0.12 watts. And 0.01 times 4 is going to give us 0.04 watts. If we add this up, we will get 0.28 watts. Now we have everything that we need to know about R1, R2, and we also have the total circuit information, and we have, very importantly, this information, total information for RA, 4 volts, 0.01 amps, 400 ohms, and 0.04 watts. Looking at our first matrix, matrix 1-P, there's all our RA information. We just put it in. Previously, all we had was these 3 resistors in parallel and the 400 ohms. Now we can start populating this table. 4 volts, 0.01 amps, 400 ohms, 0.04 ohms. We took all this information from the previous slide in matrix 2-S, and we put it in here. Now we can start calculating. This is a parallel circuit, so the rules say that voltage is the same everywhere. So I have 4 volts at R3, 4 volts at R4, and 4 volts at R5. And we know our resistance values, so now we can calculate our amperage. We have E divided by R is going to give us I. So 4 divided by 1200 is going to be 0.003 amps. The same on each one of these because these values are all the same. Our wattage is going to be 4 volts times 0.003. I times C gives us P. 4 times 0.003 equals 0.013 watts. 4 volts times 0.003, the same thing. So if we add all this up, forgetting the fact that we have rounding errors possibly, it will equal 0.04 watts. We can now take all the information from this 2 series and parallel matrix, omitting the RA values, to record every value at each resistor. This is no longer, we're not setting up this table as if it's going to be for a series circuit or a parallel circuit. We're just recording values in the table. Our totals, 28 volts, 0.01 amps, 28 ohms, 2800 ohms, and 0.28 watts. At R1, we have 12 volts, 0.01 amps, 1200 ohms, 0.12 watts, and essentially all the resistors are still 1200 ohms. We don't change them because resistance doesn't change. R2, 12 volts, 0.01 amps, and 0.12 watts. R3, R4, and R5, these are our parallel circuits. We have 0.003 amps, we have 1200 ohms, and we have 0.013 watts, and all these values are the same. Looking at it kind of together, you can see here's my RA, here's R3, R4. All those values that we just discussed are right there for the parallel matrix. Matrix 1-P, matrix 2-S gives us the same gives us the information for R1 and R2, and also RA, and if you notice, they match. This concludes the instructional portion of this module. Be sure to click in the link below to take the online quiz. This is Module 5, by the way, not Module 4. And after this, there'll be another module on voltage drop. Make sure that you come back and find that one.